So now that we have the projectile set up, it's time to get it actually moving. Now we need to realize a number of different things. Everything is timing based. Now we know our games move at 60 frames per second on average. That doesn't mean they actually do. So there may be a certain amount of time that's less than or more than that 60 frames, or that the amount of time passed in between each update. So we need to account for this, because otherwise we may end up with a situation where it doesn't actually look like the projectile is moving naturally. So we need to actually detect how much time has passed and factor that into our actual movement. Okay, so we don't want to actually treat it like it's an equal thing. We want to actually calculate exactly how much time has passed and apply that effectively. So in order to update the projectile, it looks like it's a complicated process here, and it can be complex to understand, but in reality it's very little code. In fact, it's not much code at all. It's only about 8 or 9 lines of code. So let's take a quick look at this. First thing we need to do is we need to realize that all the forces are in units of 1 second. So gravity moves at 130 pixels per second. Wind moves at whatever, in this case 0 pixels per second. So but we can actually detect how much time has passed since the last update, but that unit is actually in milliseconds. So for example, I might a total of 12 milliseconds might have passed since the last update. So 12 milliseconds, let me go down here. If 12 milliseconds pass, let's call them millis. If 12 millis pass, that's the equivalent of 0.012 seconds. Now think about that for a second. If gravity moves at 130 pixels per second, how much does it move if only 0.012 seconds passed? Well, 130 times 0.012. And that's how much we would actually apply gravity to our whole trajectory. So that's where timing comes into play. So that way, maybe the next update, 16 milliseconds pass, so 0.016. You may think, well, what's the difference between that? Well, it adds up. Those little things add up. You gotta remember, this game is moving very fast, 60 frames per second. So a lot of things can occur. So basically, we're going to scale our time in the form of seconds. So that's going to give us something like this. Now, it's not always going to be that. It's going to be however much time passed. The next piece is we need to apply the physics forces to our movement vector. So our trajectory. We need to apply physics there. But first, we need to scale those physics forces by the amount of time passed. So basically, if our physics force, as we see in this example here, has an x component of 3, which means wind of 3, and a y component of -2, that means that in reality the force looks something like this. It's got an x component of 3 and a y component of -2. That means that the actual force vector looks like, well, the actual force vector looks like that, with this nice line here. Now the problem is that is good for 1 full second. Now we want to scale that back because a full second didn't occur. Only 0.012 of a second occurred. So in reality, our vector is going to be much more like this, way down here. That's how much is actually going to be applied. Now I've got these numbers all playing with here. So what's really going to happen here is in our game we only have gravity being applied. So gravity is normally 130 pixels per second, but if we did a quick little let me prop up the calculator here. If we had 130 pixels but only 0.012 passed, that means that 1.56 pixels would be the actual value of gravity being applied. So the y component would be 1.56 pixels, which is much less than 130 pixels per second. So that's how much is actually being modified there. So anyways, so we've calculated, we know what our force vector is, and we're going to multiply that force vector by the amount of time passed. Now we're going to add this to the movement vector, the trajectory, on a permanent basis. So this is very important. the actual trajectory, the original trajectory itself, is going to be modified on a permanent basis. That gives us this approach where we add this, and then the next time we add it again, but it gets reduced, and the next time we add it again, but it gets reduced, and that's going to give us our curve by making it a permanent change. It has to be a permanent change. So basically, we're going to calculate our time. We're going to take that time, we're going to multiply it by our forces, and then we're going to take our new smaller forces and permanently modify the trajectory by those smaller forces. So let me show you that in code right here. So I've taken my time and I've multiplied it by 0.001 to put it in a factor of 1 second. So 12 becomes 0.012. Next thing we do is we're going to scale our forces by that amount of time. Right, so this is a built-in functionality, but basically it takes this time and multiplies it by the x component of forces and the y component of forces. This value is then added to the trajectory vector. So that's where we do the nose to tail thing. So going back over here, that's basically what happens when we go like this. Now we apply the force vector, which is like this, and then the result is this, and then, wow, auto update. The result is then stored back into the trajectory. That means that the new trajectory is the modified version. We can see this right here where we're saying trajectory is equal to the current trajectory plus the forces, the scaled forces. All right, so it's a reduced amount. So the new trajectory has a new value. But now that we have that new trajectory, we're actually a lot farther along. That's the most complicated process. So now all we have to do is we need to apply this trajectory to a position. Now in the code you can see that I have a position variable, and this is a vector 2. It's just an x and y component. And the reason why I'm applying the trajectory x and y to that value is that this one can actually handle decimal values. So it has a much more accurate representation of the real position of the projectile. And that's important because remember, you can't have a part of a pixel on the screen. So we need to have an accurate measurement. So things get truncated. So decimal places get cut off and whatnot, which we'll see in the next step. So basically, we have this accurate position, and we're going to add on to that the current trajectory, multiplied by the amount of time passed. Because remember, trajectory is still in scale of 1 full second. So we need to multiply it by how much time has actually passed. So 0.012, for example. Go back over here. As it says here, apply the trajectory of floating point position, a position that can handle decimals. The trajectory needs to be scaled by time. That should be much like the forces. Oops. Let me just put this back, take this off. Much like the forces were before they were applied, we got to do the exact same thing. So we have to scale the forces, and then this is done on the fly though. You can see here that I'm actually multiplying it here and then applying it directly. The trajectory is not actually being modified here. It's just doing a temporary change and taking that temporary change and applying it to the position. Here it actually stores it on a permanent basis. We're not doing that here. We're only taking the scaled value, adding it to the position and restoring it. And the last step is we have to take that accurate value of position and cast it to an integer so we get a value that we can actually draw on the screen, an actual pixel value. So if we have a x value of 31.78, that 0.78 gets cut off, so the x value will be 31. And on average, as the thing is moving, those little truncations will fade away and it'll look like it's a nice smooth experience. And that is the last bit to it. And that's projectile motion. So if we go back here and look at this whole bit of work, just to see what all's happened, basically we've created our launch trajectory, we created our force vector, then every single update we apply those two things. First thing we do is we see how much time has passed. Alright, let's scale our forces. Right here, we're scaling our forces. Now let's add those scaled forces to the current trajectory. Once we have a new trajectory, let's apply that trajectory, scaled by time, to the current position. And then cast that current position to an integer to get a screen friendly version of that position. And that's it. So when we run our program, we get our nice simulation. Now again, you're looking at 10 FPS on the video, but the actual thing is 60 FPS, so it probably looks pretty choppy to you, but it looks pretty clean on this end. And that is projectile motion, updating, drawing. You'll notice that I have some other stuff in this demo as well, which you'll see when you look at the actual code. But this stuff is just to handle things like collisions with the walls and the ground to make sure it doesn't fall through the floor and it bounces off the wall. And I'll show you what I mean by that. So if I crank up the speed really quickly, you're going to see it bounce right off the wall. Oops. Oops, that's the wind. There we go. And let's reduce the degrees. We'll put out a nice 45-degree angle. We're going to crank up the speed, and we're going to launch it, and it'll bounce off the wall. And all I do basically whenever it hits the wall, I just reverse the X or the Y velocity depending on which wall it bounced off. So it bounced off the left or right wall, I reverse the X velocity. If it bounced off the top wall, I reverse the Y velocity. If it hits the ground, I stop it moving. Now of course you could continue bouncing it if you want, but that's up to you. So that's projectile motion, everything you need and hopefully want to.